That's our f of x, and I just want to look at a connection between the sign of the second derivative and the direction of the curvature, whether the graph is curved upward or curved downward. Ultimately we'll see that. But the definition that's going to be given, let me copy and paste it here, of concavity has to do with the first derivative. That's the definition. We'll have a definition, then we'll have a theorem. The definition, if f is differentiable on an open interval I, then f is said to be concave up on I if f prime is increasing on I, and concave down if f prime is decreasing on I. So ultimately we're going to think of concavity as something about the sign of the second derivative, but it's defined in terms of whether the first derivative is increasing or decreasing. So let's look at the function, and let's work our way from left to right and see if we can decide whether f prime is increasing or decreasing. So these are the values of f prime as we move the slider, and I'm see if I can move it more slowly. If I go with bigger slider here, I can move it more slowly. There we go. As we go from left to right, negative 21.23, what's going to happen to that value? Is it increasing or is it decreasing?
Increasing.
It's increasing. It's increasing. Okay. Let me know when it stops increasing. So it looks like it's still increasing. Still increasing. Still increasing. 2.5, 2.9, 3.5, 3.7, 3.8, 3.9, 4, 3.9. There we go. So it looks like the first derivative got as high as it was going to get at 4. And so we can say the first derivative is increasing along this interval. And so according to that, according to our definition, the curve, this function right here, is concave up along that interval. So when you go from steep negative to not so steep negative, to 0 to positive, those values are increasing as they work their way along the number line. And so, so it's concave up from, I'm going to say, negative infinity, although we can't see quite that far to the left, to 0. Now at 0, what's happening to the first derivative? First derivative, f prime, it's decreasing. And it's decreasing. It gets to 0 and beyond. It's continuing to decrease, 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 decrease. There we go. So from 0 to positive infinity, it appears that f prime is decreasing. Now, when a function is increasing or decreasing, we can tell when that's happening by looking at the sign of its derivative. So if I have a function, maybe I should call it g. If I want to know when g is increasing, I look at the sign of its derivative. What's the sign of the derivative of g if g is increasing? Then g prime would be what? G is increasing, so the slope of the tangent line to g is well, positive. So, I mean, so what is the derivative of f prime? Or what's the name of the function? What's the name of the function? Like the derivative of f is f prime. The derivative of f prime is the notation, f double prime. Right, f double prime. So let's go back to the notes and let me see if I can summarize this. I need to oops. Won't let go. Eraser? That would work. Bigger eraser in another room that works better. But this will work. So here goes. Here is a f prime. Along this interval, f prime was increasing, and along this interval, f prime is decreasing. What can we say about f double prime? If f prime is increasing, its derivative, f double prime, is what? Is, well, I need to put this in the form of a multiple choice question so you know what answer I'm looking for. F prime is the red graph. F prime is the red graph, and you can see the red graph is increasing up to 0 and decreasing on the other side of that. That's f prime. F double prime is the blue graph. See the blue graph? Now the blue graph is decreasing throughout. But where f prime is increasing, f double prime is, well, it's decreasing throughout, but it's above the x-axis, so it's positive. F double prime is positive. Positive. And where f prime, that's the red graph again, is decreasing, f double prime is negative, below the x-axis. The blue graph, negative. F double prime is negative. Now I want to say something about the original function, f. The original function f is the black graph. And what I want to say about the black graph is its curvature. Curved upward, concave up. Curved downward, concave down. From negative infinity up to 0, it is curved upward. So we're going to say it's concave up. F is concave up. And from 0 to positive infinity, it's curved downward. So we're going to say F is concave down. Now it kind of starts in the middle according to our definition. We look at f prime, and we find where f prime is increasing, where f prime is decreasing. But these three are equivalent. If we're on an open interval and f prime is increasing, that means f itself is concave up and f double prime is positive. Those three are equivalent. If f prime is decreasing, we can look at the function f and realize it's concave down. We can look at the second derivative, f double prime, and see that it's negative. So those three are equivalent. So one more time at the graph, and then we'll look at an example. Black graph, to the right of 0 here, concave down. If we look at the first derivative, it's decreasing. If we look at the second derivative, it's negative, below the x-axis. And over here to the left, concave up. If we look at the first derivative, it's increasing. And if we look at the blue graph, that's the second derivative, sorry. The blue graph is the second derivative. It's above the x-axis, so it's positive. So those are the connections to make with that. We have a theorem, and basically I've already summarized the theorem in what I've said here. If f double prime is positive on an open interval I, then f will be concave up. Of course, the second derivative needs to exist, so f has to be twice differentiable. If f double prime is negative on an interval I, open interval I, then f is concave down on that interval, and that is summarized right here from top to bottom. F double prime is positive, f is concave up. F double prime is negative, f is concave down. So the definition was given in terms of f prime, whether it's increasing or decreasing. but the theorem is what we'll really use. We'll look to see, okay, we want to sketch a graph or look at or say something about a graph. To see where it's concave up, that's an interval where f double prime is positive. And to see where it's concave down, that's an interval where f double prime is negative. So we'll analyze the sign of the second derivative, and that'll tell us where the graph is concave up and where the graph is concave down. And how do I get to the next page? I could get that way. But it'd be nicer if I had full screen. Okay. Find open intervals on which the following functions are concave up and open intervals on which they are concave down. Both cases, we're going to find the second derivative and sketch a sine graph for the second derivative. So the first one, f prime of x equals 2. F double prime of x equals 0. Well, I don't know if the sine graph would be all that productive here. Where is f prime of x positive? Nowhere. It's always 0. Where is f double prime of x negative? Again, nowhere. So f is not concave up anywhere, and f is not concave down anywhere. There's no curvature at all to the graph because we know this graph. It's a straight line. Something like that. So we would say it's neither concave up nor concave down anywhere. Next one. Polynomial, not too tough to take the necessary derivatives. Negative 6x minus 6 for the first derivative, negative 6 for the second derivative. Now a sine graph might be appropriate because it's actually non-zero. If I construct a sine graph for f double prime, well, I might look for second order critical numbers. Now, with the first derivative test, you look for first order critical numbers, critical points, we also call them. We just call them critical points because we hadn't talked about the second derivative yet, but first order critical numbers are places where either the first derivative is 0 or the first derivative is undefined. For the second derivative, a second order critical number is going to be where either the second derivative is 0 or the second derivative is undefined. Well, the second derivative is constant. It's not constantly equal to 0 like it was in the previous example. So there aren't any. So if we choose a test number, the sign won't change. So I just need a number between negative infinity and positive infinity. 0 works. So 0 is my test number. So f double prime of 0 is negative 6, and that's negative. So the second derivative is always negative. It's negative at 0, and it's negative everywhere else. It's always negative 6. So what we would say is that f, since the second derivative is negative everywhere, f is concave down on the interval from negative infinity to positive infinity.
Could we also say it's convex up?
Usually we don't. Yeah, the concavity is just the direction it opens is easier to handle than the direction it closes. So I don't know, is the x. I'm going to erase that because I don't want to have to think too hard about this. When we know what the graph looks like, though, basically it's a parabola. So concave down throughout. And this is one kind of like what we looked at. Take a couple derivatives, and then we can see what's happening just kind of by inspection. If we believe that this is the graph, let's guess our way at it, and then we'll take a couple derivatives and we'll see if it makes sense. It looks like this function is concave down where?
The edge of L.
Till about, where does it stop? Can we look at it and tell where it stops being concave down? Does it stop? Come on, let me write on it. Does it stop being concave down there? It's still concave down a little bit. What about right there?
Could it be the midpoint between -2 and 5?
It might be. If 5 is there and -2 is there, what's halfway between -2 and 5? 2.5? 2.5. Oh, this rough looking grid here. Maybe about right. About right. Right there?
It seems to flip back out a little bit earlier.
Yeah. Maybe in there somewhere?
Use tangent lines.
So what we're we could do that. What we're searching for is an inflection point. We'll define this in a little bit. An inflection point is going to be a point where the concavity changes. The function's continuous there, and to the left it's concave one direction, and to the right it's concave another direction. So let's see if we can find exactly where that is. So f prime of x equals 6x squared minus 18x minus 60. F double prime of x equals 12x minus 18. If we're looking for a second order critical numbers, we would like to know where this is equal to 0. So set 12x minus 18 equal to 0. 12x equals 18. X equals 18 twelfths. Is that 1.5? 1.5. I wonder if that's the halfway point between -2 and 5. It is, okay. So 1.5. 1.5 is going to work for us. So sine graph for f double prime, 1.5. If we evaluate f double prime at 0, test number there 0, we get -18, and that's negative. And if we evaluate it at 2, f double prime of 2, we get 6. 12 times 2 is 24. 24 minus 18 equals 6. So it's positive at 2 and throughout that interval. So where we get the minuses for the second derivative, it's going to be f, the original function f, is concave down. And where we get the pluses, f is concave up. Like that. So what's the interval where it's concave down? Negative infinity to 1.5. And on intervals where a function is increasing and decreasing, the way it's defined, it is possible to include the endpoint sometimes and exclude the endpoint sometimes. But for concavity, typically we do not include the endpoints. We just define concavity on open intervals. So f is concave up on the interval from 1 to positive 1.5 to positive infinity there. The point where the concavity changes is called an inflection point, and the y coordinate of that point will be important. The next problem will ask us to do this, so I won't go ahead and do this. But 1.5, we go back to the original function f. Looks like negative 90 something would be the y coordinate of that point. But the inflection point will be important to us here in just a little bit. Close that out. I could have saved that. There's our definition. If a function f is continuous on an open interval containing the point or number, you could say, x sub 0, and if f changes the direction of its concavity at that point, then we say that f has an inflection point at x sub 0, and we call the point, that particular point on the graph with that x coordinate, an inflection point. Sometimes it's called a point of inflection, but that means the same thing. Inflection point or point of inflection, a point on the graph where the concavity changes. It's concave one way to the left, it's concave the other way to the right. So, the typical picture is this, and that's x sub 0, f of x sub 0. Looks like concave down and concave up. But according to the definition, the function must be continuous at that point, but not necessarily differentiable. So there could be a point of vertical tangency. That could happen. Oh, it's a typical example of a point of vertical tangency. Maybe something like that. So it's not differentiable there, but it looks like it's concave up right there and concave down. Some illustrations to get the idea of concavity, if it's not clear enough. Concave up holds water, a bowl like that holds water. Concave down spills water, it just falls right out. I like that for this one.
Shouldn't be the other way around.
Concave up?
Yeah, because when you go up, it's convex. It's getting wider, it's convex. Whereas going down, that's when it goes concave.
Well, the curvature is up. For a more precise definition, a function is said to be concave up on an interval if you take any 2 points on the curve within that interval, the straight line segment connecting those 2 points is completely above the curve. That would be concave up. But if it's concave down on an interval, then if you take any 2 points, maybe this one and this one, in the interval, then the straight line segment connecting those 2 points is completely below. So the below, downward. I was just saying that I don't think this particular curve would hold any water because the water would slide on out to negative infinity if there was gravity at negative infinity. But we won't go there. Anyway, inflection point. Let's see if we can find an inflection point. Find the inflection points of... Do we want the picture there in front of us to distract us? Maybe. We need a couple derivatives, and we really need to know the intervals where it's concave up and the intervals where it's concave down. So I'm going to suggest finding 2 derivatives, constructing a sine graph for f prime, so with the pluses and the minuses, so we could say it's concave up here, it's concave down here, it's concave up there, because those points, the endpoints, we actually need to know that the concavity changes. Rather, it's not enough to say the second derivative is equal to 0 at those points. We actually need to see a change in the concavity. So let's do it just like we did the previous one, except we'll take it a step further and actually find the coordinates of the points, maybe right there somewhere, and right there somewhere where the concavity actually does change. So f prime of x equals 4x cubed minus 12x squared minus 96x plus 14. F double prime of x equals 12x squared minus 24x minus 96. Hopefully this will give us some nice second order critical numbers. If we set that equal to 0, it's a polynomial, so it's not going to be undefined anywhere. If we set it equal to 0, we can factor out the 12 looks like that, minus 4 plus 2. Good. So set each factor equals 0. 12 is going to make no contribution to the zeros of this expression, but certainly negative 2, positive 4. So we'll go with this. X equals negative 2, x equals positive 4. Put the numbers in order from left to right on the number line and construct a sign graph for f double prime. Pick nice numbers, less than negative 2, between negative 2 and 4, and greater than 4. So I'm going to go with negative 3 for a test number less than negative 2, 0 for a test number between negative 2 and 4, and 5 for a test number greater than 4. Now, if we want to know where to plug these numbers in, it's a sign graph for f double prime. So we want to know, is f double prime positive or negative? So we evaluate f double prime at negative 3. And we can disregard the 12, but it's probably not that tough to multiply by 12, so I'll go ahead and keep the 12. 12 times negative 1 is negative 1, sorry, is negative 12. And negative 12 times negative 7 is positive 84. So pluses, concave up on the interval from negative infinity to negative 2. If we evaluate it at 0, f double prime of 0, we can use this expression up here, the unfactored form, and just get negative 96. That's the easiest way to find that. That's negative, so minuses, and f is concave down. And the 5, f double prime of 5, 5 plus 2 is 7. 12 times 7 equals 84. And 84 times 1 is 84. So pluses, f is concave up from 4 to positive infinity. So we want to find inflection points. There could be one at x equals negative 2, and there could be one at x equals 4. The concavity does change at negative 2. So negative 2 f of negative 2 and 4. The concavity does change at 4 from down to up. 4f of 4 are inflection points. So we just need to go back to the original function. Not fun, except maybe with a calculator. Substitute negative 2 for x. Or we could even use synthetic division if you'd like to. Substitute 4 for x and evaluate these polynomials. This is probably one nice application of synthetic division. But if anyone has them, I'll be happy to copy and paste them onto my screen here. No? Okay, synthetic division time. If I want to evaluate a function at negative 2, I can actually use negative 2 and the process of synthetic division. And maybe that's better than substituting negative 2 for x everywhere I see an x. And we can, by the remainder theorem, this works out. So bring down the 1, and we get negative 2, and we get negative 6, and then 12, and negative 36, and 72, and 86, and ouch, negative 172, and negative 178. Well, that's the point right there. This would be negative 200, it looks like. Negative 200. That could pass for the point negative 2, negative 178. Did anyone else get that? Okay, good. Let me try it with the 4. You don't have to use synthetic division for this, because if it's not a polynomial, synthetic division doesn't work anyway. I would suggest just type it into your calculator and see what the calculator says. All right, so negative 718. Sounds good. So that's the point 4, negative 718. So those are the inflection points. So it's points on the original graph where it's concave one direction to the left, it's concave the other direction to the right. And there are applications of this sort of thing in economics. Point of diminishing returns is an inflection point. You keep putting more and more into a system, but as a proportion of what you put in, you get less and less out. You still get more out, but not as much in proportion to what you're putting in as you previously did. Okay. In case you worry that as a rule, I do problems in class that are too easy and problems on the test that aren't too easy. Here's one that's maybe a little bit more on the challenging side. Oh, good. A rational function. Find the inflection points of this one. X cubed minus 19 over x minus 3. What I've done here to make the differentiation easier, we have to take two derivatives, and I really don't want to hit this with the quotient rule once, much less twice. So what I've done is I've used either polynomial division or synthetic division to rewrite this. I think synthetic division is probably the way to go. If we're dividing by x minus 3, that's one of the cases where synthetic division works. If you're dividing by x minus a number or x plus a number, you can use synthetic division. So if you go with 3 and 1 for the x cubed and 0 for the missing x squared term and 0 for the missing x term and negative 19, then you're going to have a 1 and a 3 and a 3 and a 9 and a 9, and a 27, and an 8. So the quotient would be the x squared plus 3x plus 9 that you see there. The remainder is 8, so you write plus 8 over the divisor, 8 over x minus 3. So we can rewrite it like that. It's much easier to differentiate that way. If I do one more thing, if I say f of x equals x squared plus 3x plus 9 plus 8 times x minus 3 to the negative 1, it's even slightly more easier. It's easier still than it was previously if we write it write it as multiplied by x minus 3 to the negative 1. That way we can use the generalized power rule on that. So f prime of x equals 2x plus 3 minus the negative 1 gets multiplied by the 8. And then we have x minus 3 to the negative 2. And the chain rule says multiply by the derivative of what's inside the parentheses. What's the derivative of x minus 3? 1. 1. So don't forget to multiply by 1. There. We can simplify that if we want to, but we've got to take another derivative, so I'm going to go ahead and do that. F double prime of x equals 2 plus the negative 2 gets multiplied by negative 8, and we have positive 16 x minus 3, and we subtract 1 more from the exponent, and again multiply by the derivative of what's inside the parentheses. Again, we multiply by 1. Well, we're taking another derivative. Yeah. So f double prime of x equals 2 plus 16 over x minus 3 quantity cubed. Now, I've thrown this one in here because most of my examples, I say, well, this is differentiable everywhere, so we don't get critical numbers from values where it's undefined, but this one actually has a value where it's undefined. So for our second order critical numbers, second order critical numbers, it could be where f double prime of x equals 0. And where does that happen? 2 plus 16 over x minus 3 quantity squared equals 0. that would be where, and I just don't have room, so I'm going to see if I can work on 2 pages here. 2 pages at once. So that'll be where (16 over x minus 3 quantity squared equals -2).
Shouldn't be quantity cubed.
Thank you. Is it? Yes, absolutely. Thank you. Sorry about that. There. What's the nicest next step? I want to think maybe reciprocate both sides. X minus 3 quantity cubed over 16 equals -1/2. Then multiply both sides by 16. X minus 3 quantity cubed equals -8. Take the cube root. Yes. X minus 3 equals the cube root of -8. We're just concerned with real solutions. So x minus 3 equals -2. So x equals 1.
A lot of work.
X equals 1. So that's our first order critical number. Oh, there's another possibility. See, it could be that f double prime of x equals 0. It could also be that f double prime of x is undefined. And this one's easier to find. It's undefined where?
When x minus 3 cubed is 0?
Yes. And x minus 3 quantity cubed is equal to 0. Take the cube root of both sides when x minus 3 is equal to 0. So that's when x equals 3. 3 is the 0 of the denominator, so that causes it to be undefined. So if we look at our sign graph for f double prime, we're going to have a -2, and we're going to have a +3. Now there's no hope of getting a critical point, there's no hope of getting an inflection point at 3, because the function itself is undefined at 3. It has to be defined, it has to be continuous at a number to get an inflection point there. Nonetheless, we want to have that 3 there, because if we check for the concavity to the left of -2, and we just choose a test point, a test number, to the right of -2 without regard to the 3, if the concavity here is different from the concavity here, I might make the mistake of putting all pluses across there or all minuses across there. Depending on where I pick the test number, I might pick it between -2 and 3, or I might pick it greater than 3. So I need the test number there, even though there's no hope that that could be my inflection point. It'll tell me whether or not there's an inflection point at -2. So let's go with -3 and 0 and 4.
Can you say again why it's -2 and not 1? Sorry, I messed up.
It's 1.
It is 1. Okay.
Where was I seeing that? I guess I was seeing the -2 there. I don't know where I was seeing the -2. Thank you. It's 1. Everything I said is correct except with the different numbers. 0, 2, 4. How about that? 0, 2, 4. Let's evaluate the second derivative at each of these numbers. F double prime of 0. Where's the expression for f double prime? It's that 2 plus 16 over x minus 3 quantity cubed. So that would be 2 plus 16 over -3 cubed. 2 minus 16/27. The exact value is not a big deal, but I guess I can go ahead.
I think 70 over 27.
Well, it'd be 54/27 minus 16
Oh, minus.
over 27.
So it'd be positive.
So it would be positive. What's 54 minus 16? 38. 38 27ths. That's positive. So it's positive there. Concave up. How about 2? F double prime of 2. That's going to be 2 plus 16 over 2 minus 3, quantity cubed. That's going to be 2 plus 16 over negative 1, or negative 1 quantity cubed. So 2 minus 16 is negative 14. So concave down. And 4, F double prime of 4, 2 plus 16 over 4 minus 3 quantity cubed, 2 plus 18, 2 plus 16 equals 18, and that's positive. So the point I was trying to make earlier, is 18 okay? The point I was trying to make earlier, it would have gone better if I had gotten the critical numbers correct, was that if I don't include the 3, when I test the interval to the right of the 1, if I pick 2, then I'm good because it'll give me the correct concavity immediately to the right of 1. But if I say, okay, let's just pick a number greater than 1, how about 4? It'll make me think that it's concave up immediately to the right of 1, and so that the concavity does not change. So the 3 is not an location of an inflection point, but I have to use the 3 to make sure of the concavity in each of these intervals. The concavity does change at 1. The function is continuous at 1. So f has an inflection point, or let's say the inflection point, one comma whatever f of 1 is. So we have to go back to the original function and figure out what f of 1 is. 1 cubed minus 19 over 1 minus 3. So negative 18 over negative 2. 9. So the point 1, 9. That's the only inflection point that this function has. Let's go to the graph and see if it looks like 1, 9 is where the concavity changes. Maybe. Does it look like it's concave up to the left of that and concave down to the right of that? And then on the other side of the vertical asymptote, it's concave up right there.
Or convex down.
All right.
Can you go back?
Oh, yes. Let's go right there. Is that good? Sure. Next, some transcendental functions. I want to make sure I give enough attention to transcendental functions. Sometimes I neglect them. I don't want to do that. Sure. Inflection points of x e to the negative x. And cosine x. Two derivatives, f prime of x equals, what rule do we use to take this derivative? Product rule. We have a product. So it's the first times the derivative of the second. And technically we're using chain rule to find the derivative of e to the negative x. The derivative of e to a power is e to that power times the derivative of that power. So this is the first times the derivative of the second. And then it's the second times the derivative of the first. E to the negative x times the derivative of x, which is 1. So negative x e to the negative x plus e to the negative x. Before taking the second derivative, we could factor out the e to the negative x or not. Anyone have a preference? Factor out the e to the negative x or not? Factor it? Factor it? Okay. It's going to involve the product rule in any case. We'd have to repeat derivative x e to the negative x, and then we'd also have to add the derivative e to the negative x. So just factoring here, f prime of x, no derivative yet, would be negative x plus 1 times e to the negative x, I guess with or without the parentheses around the e to the negative x. Those aren't a big deal. But of course we need them around the negative x plus 1. Now the derivative, second derivative, f double prime of x equals the first times the derivative of the second, so negative x plus 1 times negative e to the negative x, first times the derivative of the second, plus the second times the derivative of the first. Where is the second? E to the negative x times the derivative of negative x plus 1 is negative 1.
Isn't the derivative of e to the negative x e to the negative x? Okay, yeah, I see what you did there.
Yeah, got to multiply by that.
I just
Negative.
looked at the and then I looked at it and thought.
Now, one more time, factor out. We're going to have to set this expression equal to 0 and solve for x. So having it in factored form is very, very important. Let's factor out e to the negative x here. So f double prime of x equals e to the negative x
Minus 1.
yes, x minus 1 minus another one. Yeah, this negative basically flips these two signs right here. And so you have x minus 1, and then this minus 1 comes right there.
You couldn't go ahead and multiply like and make it negative e to the negative x, and then factor it out as negative e to the negative x.
That'd be okay. You'd have a 2 minus x on the inside instead of x minus 2. That'd be fine. So x minus 2 times e to the negative x. All right. Not going to be room for this one, so I'll scratch that out. Let's set this equal to 0. We need a sign graph for f double prime. So x minus 2 times e to the negative x equals 0. X minus 2 equals 0, or e to the negative x equals 0.
Which e, yeah, right?
That's right. E, exponential function, cannot be 0. So either x equals 2 or nothing. No solutions there. So 2 is the only second order critical number for us in our sign graph for f double prime. So pick a number less than 0, less than 2, 0 is less than 2, or pick a number greater than 2. Greater than 2, I don't think you see any special numbers. 71.
I'm happy with 3.
71 would work. Maybe 3. So f double prime of 0 is going to be 0 minus 2 times e to the negative 0. So that's going to be negative 2 times 1. or negative 2. Less than 0, so we get minuses. Concave down. Now the 3. F double prime of 3 is 3 minus 2 times e to the negative 3. And it's going to be 1 times, well, here's the thing. The function e to the x has all positive real numbers in its range. Not 0, nothing negative. So we know, since e to the x is always positive, e to the negative 3 is positive. It's 1 over e cubed. Fairly small number. But it's positive. So this is 1 times e to the negative 3, and it is positive. So pluses. Concave up. This function is continuous everywhere because x is continuous everywhere and e to the negative x is continuous everywhere and the product of continuous functions is continuous. So it's continuous in particular at x equals 2. And so there's an inflection point at 2 because the concavity changes. It changes from down to up at 2. So 2f of 2 is an inflection point. And what is that? Go back to the original. F of 2 equals 2 times e to the negative 2. 2 over e squared. I want to put a box around it. But 2 over e squared is what I need. So 2 comma 2 over e squared. E squared is 7 point something. So 2/7. A little bit.
You'd be okay with 2 over
2 over e squared is good. Or punch it up on a calculator would be okay. Oop, I was looking for the graph. So does it look like the concavity changes at 2? Would you say it's concave down to the left of that and concave up to the right of that? Concavity changes there at 2. Cosine x. What is the first derivative of cosine x?
Negative sine.
Negative sine x. And take one more derivative. What's the derivative of negative sine x?
Negative cosine.
Negative cosine x. So the second order critical numbers for cosine x are exactly the zeros of cosine x. So the second order critical numbers happen at the x-intercepts. Right there. I guess that would be pi over 2. And there. 3 pi over 2. I suppose I should come up with a nice expression for that. So b, f of x equals cosine x, f prime of x equals negative sine x, f double prime of x equals negative cosine x. If we set negative cosine x equals 0, that's precisely when cosine x is equal to 0. So x equals pi over 2 plus k pi?
I think, is it 2K?
We could do 2k pi, but then we would separately have to say 3 pi over 2 plus 2k pi. So if we just say pi over 2 plus k pi, where k is an integer, then that would do it. The inflection points since we know they happen at intercepts, the inflection points would be pi over 2 plus k pi, comma, 0, where k is any integer. So the inflection points for the cosine function are exactly the x-intercepts, because the concavity does change. Now, I kind of waved my hands at that because I didn't do the sine graph and try to convince everybody that it did in fact change. It seems intuitively clear that it's concave down, then it's concave up, then it's concave down, then it's concave up. Does more have to be done to convince you of that, or is that enough? Thank you.
Does more have to be done to convince you of that on a test?
No. Not this case. All right. All right. So, transition away from inflection points a little bit. I guess we can get going again. We are about to look at the second derivative test. Do you remember anything? I haven't graded these pages on the test yet, so I don't know. But do you remember anything about the first derivative test?
Yes, I was so confused.
So you remember it was confusing?
Yes.
Do you remember anything else about the first derivative test? What does it test for? What is it good for?
Are you increasing or decreasing?
Well, you need to know whether you're increasing or decreasing. If you're increasing up to a point and then decreasing away from it, then you know you have a relative max there.
Oh, yeah.
And then if you're decreasing down to a point and increasing away from it, then you have a relative minimum. So basically, first derivative test tells you about relative extrema. Do you have one or not, and if so, what kind? Second derivative test is going to be used to get the same information, but the hope is with a little bit less work. So the gain is maybe it's less work. The loss is that maybe it doesn't always work. So we're going to hope that the second derivative test is going to work for us, and when it does, it's going to be a good thing. So imagine the graph looks something like this. Looks something like this, and there is a horizontal tangent line at x sub 0, and that means, so it's nice and smooth, it's got to be smooth, twice differentiable, so at least that's smooth. That means that f prime of x sub 0 equals 0. First derivative is equal to 0, horizontal tangent line. But look at the graph. It's concave which way? Concave up. That's an indication that f double prime of x sub 0 is positive. So if we have a function that's twice differentiable, at this point, f prime is 0, horizontal tangent line. F double prime is positive, concave up. It has a relative what? It has a relative minimum. Okay, what this means is to demonstrate that a function has a relative minimum at a particular point, we don't have to pick a test number out here and a test number out here to see if we have minuses or pluses on both sides. We just need the values of the function and its derivative and its second derivative at x sub 0. Actually, not the value of the function, just the first derivative and the second derivative right there. So a little bit less work than the first derivative test. On the other hand, maybe the graph looks like this. There is a horizontal tangent line at x sub 0, so f prime of x sub 0 equals 0. And f double prime of x sub 0, if it's concave down, that's negative. F double prime of x sub 0 is negative. Now, based on that, we can say it has a relative minimum. We don't have to say what's going on to the left or what's going on to the right. Like we do in the first derivative test, we just need to know what's going on at x sub 0, and we could say relative minimum. Relative maximum, whatever that word is there. Sorry. Relative maximum. Right there. Sorry about that. Relative maximum. Now, the downside of the second derivative test is that, well, the two downsides. It has to be twice differentiable. You can recall maybe that we applied the first derivative test to a function that looked like that. It was first derivative was positive to the left, negative to the right, and we concluded that it had a relative maximum just based on the first derivative test. it has to be smooth in order to use the second derivative test. Most functions we deal with are smooth, so that's okay. The other thing is this. Suppose f prime is equal to 0, so that there's a horizontal tangent line, but f double prime is also equal to 0. That can happen. We cannot conclude that it doesn't have a relative extremum, because there are examples where it does. F of x equals x to the 4th power. It's a flatter bottom than a typical parabola, right there. So f prime, 4x cubed, is equal to 0 at 0. F double prime, maybe 12x squared, is equal to 0 at 0. So it doesn't tell us, the test is inconclusive, but it does have a relative minimum there. Flip it upside down. F, I don't know, maybe g of x equals negative x to the 4th. Like that. G prime of x is 0, G prime of 0 is 0, G double prime of 0 is also 0, but it does have a relative maximum. And then h of x equals, I don't think I have to go to the 5th, I think the 3rd power will do this for me, x cubed. There we go. H prime of 0 equals 0, horizontal tangent line. H double prime of 0 is also 0. I think it's 6x, 3x squared, 6x, I believe it is also 0, but it does not have a relative maximum or a relative minimum. So when f prime of x is equal to 0 and when f double prime of x is also equal to 0, the function may have a relative maximum, may have a relative minimum, it may have neither. The test is inconclusive. We just don't know. So what we do in that case is we appeal to the first derivative test. Okay, when the second derivative test is inconclusive, apply the first derivative test. And what we would see is this. For this first picture, what we would have, to the left we would have minuses because it's decreasing. And to the right we would have pluses because it's increasing. And we would conclude relative minimum based on the first derivative test. If we looked at this one right here, to the left we would have pluses. And to the right we would have minuses, and we would conclude relative maximum based on the first derivative test, even though the second derivative test gives us nothing. And if we looked at this one, there would be pluses on both sides because it increases going in, it increases going out. And we would conclude neither relative minimum nor relative maximum if we applied the first derivative test. But sadly, the second derivative test would not apply to, would be inconclusive for any one of those three functions. So when it works a little faster, more efficiently than the first derivative test. When it doesn't work, we fall back on the first derivative test. Use the second derivative test to analyze critical points. Basically, we're going to use the second derivative test to analyze the first order critical numbers. We're not worried about concavity here. We spent the whole first 45 minutes, no, longer than that. It was an hour. It doesn't seem nearly as long to me than it does to you. So the first hour and 10 minutes talking about concavity. But now we're just talking about first order critical numbers. So zeros of the first derivative. So we don't need the second derivative yet. We will eventually. F prime of x equals 12x cubed minus, I want to say 84, x squared plus 180x minus 108. We need the zeros of this. I guess we could factor out a 12. F prime of x equals 12 times x cubed minus 8x squared plus 15x minus 9. I think this is the same function that we previously... Maybe not. Maybe not. We've never seen this before. Does it look similar? It might be similar. Let's look. I'm going to lose the 12, and I'm just going to say minus 8x squared plus 15x minus 9. Zoom 6. I think I messed that up. 12 times 7. 12 times 7 is 84, yes? Try that. Aha. That picture is familiar. Remember this one? It had zeros at 1 and 3, and we looked at it and we eventually concluded that f prime of x was equal to 12 times x minus 1 times x minus 3 quantity squared. We went there, we did that. So we don't have to retrace those steps. So the first order critical numbers are x equals 1 and x equals 3. X equals 1 and x equals 3. Now we actually applied the first derivative test to this, but let's see if we can apply the second derivative test. Well, we need the second derivative. I'm going to go back to, well, I guess right here. F double prime of x equals 36x squared. Looking at the minus 168x plus 180. What is the greatest common factor of 36, 168, and 180?
36.
36, that's wonderful. F double prime of x equals 36. Oh, I got my hopes up there. 4? 12? 12? 12, okay. So 12, and then we have a 3x squared minus 14x plus 15. Seems okay. Okay. So f double prime of 1. Is it positive? Is it negative? Is it 0? Yeah. 12 times 4? Is it 48? So it's positive. So what does this mean? Horizontal tangent line, because f prime of 1 equals 0. Concave up, because f double prime of 1 is positive. So relative minimum. So f has a relative minimum at x equals 1 according to the second derivative test. Let's try f double prime of 3. That's 12 times 3 times 3 squared minus 14 times 3 plus 15. That's going to be 12 times 9 minus 42 plus 27. Yes, thank you. Sorry. 27 I say that's not going to add up to 0. 27 plus 15 is 42. 42 minus 42 is 0. So 12 times 0 equals 0. And second derivative test is inconclusive. Yes, exactly right. We're using the second derivative test to analyze critical numbers obtained from the first derivative. We're trying to get the same information as we would get from the first derivative test. We're just using the second derivative to do it instead of using the first derivative to do it. It's the same information. First derivative, relative minimum, relative maximum, and we're looking at the same the first order critical numbers when we do this. It's confusing as heck, I think, because we start off this section looking at second order critical numbers for concavity, and then all of a sudden we downshift and go back to first order critical numbers, but we're still calling it the second derivative test. So I apologize, it's intrinsically confusing, or maybe it's me, I don't know. But to me, the way it's laid out is unfortunate.
Can you just go over one more time real quick? How we know F has a relative minimum at x equals 1?
Yes, we know this. We see what's going on here. There is a horizontal tangent line, and what tells us there's a horizontal tangent line is that f prime of 1, we put in the 1 right there, we get 0. So f prime of 1 equals 0. That tells us horizontal tangent line. And then we look at the second derivative, f double prime of 1, and we're wondering, is it positive, is it negative, or is it maybe 0? In this case, it turned out to be positive, and what that told us was right at that point, the graph is curving upward. If it had been negative, it would mean the graph is curving downward, and we would say relative maximum. But since f prime is positive, it told us concave up right there. So it's curving upward, and so it has a relative minimum there. In this case, it is an absolute minimum. The minimum value of the function on the interval of negative infinity to positive infinity. This one looks like a good one to use something like GeoGebra for. So you can see, let me just kind of point at the graph. I'm not going to take this function and try to calculate its derivative. In fact, 2:05 or 2:10, what's the official dismissal time? Is it 2:10? Okay, so we can get 5 more cents worth of math, I guess. So here we go. The number of individuals on a secluded college campus who have been infected by a flu virus is modeled by this logistic growth function here, where y of t is the number of students infected at time t in days, starting with t equals 0. So if we just plug in 0 for t, when this function, 0 for t, what happens is, and I probably need to write on this, 0 for t, we get e to the 0 is 0, e to the 0 is 1, yes? E to the 0 is 1. 799 times 1 is 799. 1 plus 799 is 800, and 800 divided by 800 is 1. So we start off with 1. Yes, 1 zombie virus coming back to the campus after a break or whatever, and at such time as it happens. Okay, I can see the whole thing now. At such time as it happens, the number of people infected is low. As time passes, there are plenty of folks who are susceptible to the virus, so it increases and increases and increases. Now, when the number of people infected is low, it's not increasing all that rapidly because there are not many people who have it who are able to share it. But as the number grows, then it increases more and more rapidly like that. Now, at some point, the number of people who've not yet been infected, but who are nevertheless susceptible to it, begins to diminish. So even though more and more people have it, a lot of folks have it around day 7 or 8. Who has it around day 7 or 8? like, well, this is the number 400 people are infected with it around day 7 or 8. So you'd think it would just be really like doing this. And I guess if there's a larger population, it's going to keep doing that. But there are only so many people in this secluded college campus. So at some point, the growth rate diminishes right in here somewhere. And then from that point on, only so many people who are going to get it can get it. So it grows more slowly. So that's the function itself. If we look at the derivative of that, the point where the growth rate is as great as it's going to be, where it's as steep as it's going to be, is the maximum value of the derivative. That's the maximum value of the derivative. It's not going to grow faster than it's going to grow right there. And then after that, the derivative is less because it's growing less and less fast, less and less rapidly. So the original function, the first derivative, and we can see the 0 of the second derivative. There's a second derivative over there. 0 of the second derivative, second order critical number, is the location of the inflection point. Right there, day 7 point something, that's where the inflection point is. When we set the second derivative equal to 0, solve for t, that's what we get. Let's see, where is the original function concave up? Concave up, that means tomorrow it's going to grow even more rapidly than it did today. So f prime is increasing, it's concave up, and that's where the first derivative is positive. Y double prime of t is positive from there to there. But once it gets to right there, relax, tomorrow it's not going to grow as rapidly, not going to spread as rapidly as it did today. The first derivative is negative, and so it increases less and less rapidly. So that's when y double prime of t is negative. So that's kind of a connection across the function, the first derivative, and the second derivative. For what that's worth. Hopefully it's worth something.